This next lesson in mechanics is all about applying what we've learnt already to scenarios involving pulleys. So I've got some images here of what I mean by a pulley. So I've got one here on a table where we've got two masses and they're just connected by a string which rolls over a pulley. So as mass 2 falls to the floor, mass 1 is going to accelerate to the right. Okay. I've got another example here of like a winch with a pulley. This looks like it's on a barn or something like that. So you could use it to hoist hay bales into your barn. And I've also got an example here. This is from Amsterdam. And if you go to Amsterdam and you go on one of their river cruises or something like that, you will see that loads of the houses have got pulleys attached to the very top window of their house. And the reason for that is the houses there are very, very tall and very, very thin. And they are on the river as well. So the only real sensible way to get furniture into their house is to use a pulley, and they will lift up things. I don't know what this is. It might even be a fridge or a wardrobe or something they're lifting up here. And that's the best way to actually get the furniture into their house and then through the window. So they are very useful things, and we're going to learn about how we can apply what we've learned so far to systems involving pulleys. So I've got an example here. This is just a vertical pulley, so this is more like this example here. This object at the top is the actual pulley, and then I've got two masses, one attached to either side of it. Okay, and then the string passes over the top of the pulley. I've got the masses of the two objects. One has a mass of 6 kilograms, the other has got a mass of 2 kilograms. And we've got to find the acceleration and the tension in the string. Okay, and we're also going to talk about what are our assumptions and what is the force on the pulley itself. So the first thing to do is just label all of the forces involved in this diagram. So I've got the weight, let's put the weight on here, of 6g. There will also be a weight here of 2g. There's also going to be some tension in the string. The tension in the string here is going to be upwards. I'm just going to label it as T, because the tension in the string is stopping this object falling to the ground. So therefore it must be upwards. It's the same on the other side. The string stops the object falling to the ground, so T is also going to be upwards here. Okay. If we consider it from the pulley's point of view, there is actually a force downwards as well, which is T. So we get these sort of opposing T's, which is a bit like when we looked at the tow bar questions when we did trailers earlier on. And the reason for this is imagine you are a pulley and you've got two weights attached to you, maybe one on each arm, there's going to feel like a force downwards. Okay, so there is a force on the pulley here of these T's. Now, just like we did for the car and trailer problems, we're going to consider each of these objects separately. So we're just going to consider P first of all. Okay. Now, before we actually analyze the forces, we need to decide which direction it's moving. Obviously 6 kilograms is heavier than 2 kilograms, so the whole system is going to accelerate that way on that side. Meanwhile, the right hand side is obviously going to accelerate upwards. And as long as it's an inextensible string, they will accelerate at the same rate. So I'm just going to label them both A. Now, if we consider the forces just on P, so just here, then I'm going to resolve downwards, just because that's the direction it's accelerating. So I'm going to get 6g minus T equals 6a. So force is mass times acceleration. So 6g minus T equals ma. If I do the same for object Q, this one I'm going to resolve upwards because that's the way that it's moving. So I've got T minus 2g is ma, so that's 2a. And now I've got a pair of simultaneous equations that I can solve to find a and to find t. So what I'm going to do is I'm going to add the two equations together. The reason for that is because then that eliminates t. The plus t and the minus t eliminate each other. So I'll then be left with 6g minus 2g, which is 4g. And then that equals 8a. So a is going to be 4g over 8. Well, that's half g. So what's that, 4.9? Yes, 4.9 meters per second squared. So that's our acceleration. we can find t just by plugging that back into either equation. So I'm going to substitute it back into back into q, this equation here at the bottom. So it'll be t minus 2g equals 2 times 4.9. So that gives me 29.4 newtons. If you substitute it into the other equation, you would still get the same answer, okay, because it's the same value of t. So that's the general strategy in these questions, is form an equation for P, form an equation for Q, and then you can solve them simultaneously to find T and to find A. Now, what were our assumptions here? Well, the first thing that I mentioned was that it's an inextensible string. So that means the string does not stretch, which means that they accelerate at exactly the same rate. The other assumption we've made here is that the pulley is smooth. Smooth implies that there's no friction. And if there's no friction, the tension on both sides is going to be the same. Okay, because friction is a force, so the force would affect the other forces. So if there's no friction, then T would be exactly the same on both sides. So it's a perfectly smooth pulley. Other assumptions we've made, things like no air resistance, we haven't modelled that at all. And we've considered them both as particles, so we haven't considered their size either, or the dimensions of these objects either. Okay, here's one for you to do. So same setup, two different masses. I want you to find the acceleration, the tension, and I also want you to calculate how far does P move in the first 2 seconds. Okay, so I'm going to do the same thing as before. I'm just going to label all my forces first of all. So I've got 8G, tension up here, tension here, 3G downwards here, and I've got a tension here and here. Okay, the direction it's accelerating is going to be downwards this way, and this side's going to move upwards, speed A. Now let's solve it. So let's do forces on P first of all. I'm going to resolve downwards. So I've got 8G minus T equals 8A. And the forces on Q are going to go upwards. So I've got tension pulling it up, its weight pulling it down, and that equals MA. So that's 3A. Solve these simultaneous equations, so I'm going to add them together. So I get 5G equals 11A. So A is going to be 5 times 9.8 divided by 11. So that is 4.45 meters per second squared. And then substitute that back in to find the tension. So I'm going to substitute that back into Q. It was 4.45 recurring, so I'm going to substitute that in. So I get tension as 42.8, if you round it, newtons. Okay, so there's our acceleration, our tension. I forgot to speak about the force on the pulley in the last one. I mentioned these two T's here, but I'll talk about it for this example instead. So the force on the pulley, well, it's simply going to be this T plus this T downwards. So it's going to be 2T, or in our case, that would be 2 times 42.8. So 85.6 newtons downwards. Okay, that might be useful to know, because you might need to know, well, depending on how heavy these objects are that I'm lifting with my pulley, that might affect what material I make my pulley of. So it is important to consider that if they ask you to. The last bit of my question was, how far does P move in the first 2 seconds? So this is more of a SUVAT question. We want to know how far it moves. So we want to find S. In the first 2 seconds, we know the acceleration we just calculated was 4.45. The other thing we know is it starts from rest. Okay, so we've got S, U, A, and T. So S is ut plus half at squared. If we substitute these values in, well, ut is going to be 0, so it's just half times a times t squared, so 8.9 meters. Okay, so that's quite common as well, that they link these into SUVAT questions because we've now got an acceleration, so they can start asking you questions about that. Okay, here's a slightly different context. So we've got two particles of 0.4 and 0.8, but this time one is on a table. So this is more like the setup on the first page we had this one here, one object on the table and one hanging off the side. That's the sort of case we're going to look at now. So I'm just going to draw a diagram for this. That's my table. We've got a pulley at the end of it. Got an object here. So particles A and B, 0.4 and 0.8. There's the string going to the pulley. Okay. Particle A is on the table and it's 4.5 meters from the pulley, which is fixed to the edge of the table. The string passes over the pulley and B hangs freely with the string taut 0.5 meters above horizontal ground. Let's draw a straight line, shall we? So it's 0.5 meters. A frictional force of magnitude 0.08 g, I'm actually going to calculate what that is. 0.08 times 9.8 is 0.784, opposes particle A, so we can put that on here, 0.784. So that's just from friction. And the system is released from rest. Find out the acceleration of the system first of all. So, assuming this is an inextensible string, they're going to accelerate at the same rate. B is going to accelerate downwards, and A is going to accelerate to the right. Okay. Let's do the same as we did before. Let's make an equation for A and an equation for B. So my equation for A, I'm going to resolve to the right because that's the direction it's accelerating. There's going to be a force in the string of T. So it's going to be T minus 0.784 equals ma, so 0.4a. For B, I'm going to resolve downwards. So we've got this weight going downwards, which is 0.8g, and there's a tension upwards, just like in the last pulley question. So there's a tension upwards. So we have 0.8g minus t equals 0.8a. And again, we can solve these equations by adding them together. So I will get 0.8g, which is 7.84, minus 0.784. So that'd be 7.056 equals 0.8 plus 0.4. So that's 1.2a. Okay, so that's what I get when I add these two equations together. And I can solve that to find a. So I get 5.88 meters per second squared. Okay. Part B. I could find t as well if I wanted to, but it doesn't actually ask for that. But I could find t by putting this back into either equation if I wanted to. Part B, the time taken for B to reach the ground. Well, it's got to move 0.5 meters. It said it was released from rest, so u is 0. The acceleration we just worked out was 5.88, and we want to work out the time. Okay, so we've got 0.5 equals, well, ut would be 0, so it's going to be plus half times 5.88 t squared. And we can solve this to find t. I get 0.41 seconds. Okay, so that's just a pretty basic SUVAT question. Okay, part C. The total distance travelled by A before it comes to rest. Okay, well this is a slightly more complicated question than it first seems. There's two different sections of motion here. The first thing that's going to happen is object B is going to fall to the ground. That's what we were thinking about over here. So it's going to move 0.5 meters downwards. So I'm just going to make a note of this. So I'm going to say B moves down 0.5 meters. Therefore, I'm just going to use the symbol for therefore, A moves 0.5 meters to the right. Okay, because they're connected. However, now that B is on the floor, B is just sat on the floor. B is no longer helping pull A along. Okay, so I'm going to write, actually I won't write this down, I'll just say it. So now that B is on the floor, it doesn't have any impact on object A. However, A isn't just going to magically stop. A is still going to keep going a little bit, isn't it? So now all we've got is just object A moving along the table, but then it's got some friction slowing it down. Okay. So what we've got to work out is what is the rate at which A is slowing down. So we've got a box, this is box A. The only force on it now is just friction, 0.784. There isn't a force forward anymore because there's no tension in the string anymore because this object B is just sat on the floor. So it's not helping pull it along. So there's no more tension in the string. If I resolve this to the right then to find its acceleration now, that would just be minus 0.784. That's the only force on it. And that's 0.4 A. So A now is minus 1.96. So that's the rate that object A is now slowing down at as it just slides along the table having friction acting on it. Okay. So I've got an acceleration now. I want to find a distance, but I don't really have any other information here. I know that final speed is going to be 0, I suppose, because I know it comes to rest. But I need to find out some other information. So I'm going to try and calculate how fast it's moving when B hits the floor. Okay, so that's like its initial speed for when it's acting under friction. So let's work this out. So U was 0. This is thinking right back to the beginning now. The initial acceleration was 5.88 when it was being pulled along by B. And I want to try and find what speed did it reach when B hit the floor. So I'm going to try and find V. And we know, and the distance it moved in that period was 0.5 meters. So I can use V squared as U squared plus 2AS. So that's 2 times 5.88 times 0.5 square rooted. So its final speed was 2.425 meters per second. So that was the speed that it reached when B hit the floor. So now we know a bit more about this sort of second period of motion. We know that its initial speed was what we just worked out here, 2.425. We know its final speed, because we want it to come to rest, was 0. We know its new acceleration, or in this case it was actually a deceleration, was minus 1.96. Okay, because it's being slowed down by friction. And we want to calculate how far does it move in that time. And we can then calculate S. S is 1.5 meters. Okay, so in total, it moved 0.5 meters to the right, whilst B was falling to the floor, and then it moved an extra 1.5 meters just under friction. So sort of it was moving like under its own speed that it had built up, and then it was just being slowed down by friction. So in total, that is 2 meters it has moved. Okay. So there we go. It's a slightly more complicated question. You've got two different sections of movement, but you've got all the information you need to work it out. And we're going to look at another similar question to that in a moment, but on a vertical pulley. Okay. So in this question, I've got a vertical pulley. And the question is that I've got to solve is find the maximum height reached by object Q, so that's the one on the right, above the floor. And you can see here they've got two different masses. P starts 1 meter off the floor and Q starts 1.5 meters off the floor. Now let's just think about what's going to happen here in general before we start going into any calculations. Object P is going to accelerate downwards. Object Q is going to accelerate upwards because P is heavier than Q. P is going to hit the floor and Q is still going to keep going. It's not going to magically stop. So we've got one period of motion where P moves down 1 meter, so therefore Q would move up 1 meter, but then Q is going to do like an extra little hop once it gets to the top. Okay, it's not just going to go up and then stop. It'll go up. When P hits the floor, it will keep going a little bit up to its maximum height. So it does like an extra little hop when it gets to the top. So let's think about what information we need to calculate here. The first thing we're probably going to need is the acceleration. So let's find that in the normal way that we would do that. So for object P, let's draw on the forces. So I've got 3g T, do the same for Q. Okay, so for object P, I'm going to resolve downwards. And I've got 3g minus T equals 3a. For object Q, I'm going to resolve upwards. And I've got T minus 2g equals 2a. Add the equations together. So it's going to be 1g equals 5a. So a is 9.8 divided by 5. So 1.96 meters per second squared. Okay, let's just write that on my diagram. So that's the initial acceleration when I let go of these. Okay. We know that P is going to move down 1 meter and Q is going to move up 1 meter. So let's maybe label that on our diagram. It's going to move up by 1 meter first of all. And then we're going to do this extra little hop of distance. I'm just going to call it distance x. Okay. So this moves down, this moves up, and then it does an extra bit. So we need to think about, what do we know about this little extra bit here? Well, we know that its final speed up here, because remember it does this sort of shape, like we talked about when we did Suvat and we threw objects into the air. Up here, its final speed is 0. So we know that v equals 0. We know that the acceleration would now just be gravity, because it's no longer being pulled by the string, because P has just hit the floor. So there's no more tension in the string. So its acceleration would just be minus 9.8. So v is 0. A would be minus 9.8. The distance would be x, that's what I'm trying to work out. But I don't have a time for this, how long this takes, and I don't have an initial speed. But I think I could probably work out an initial speed, because the initial speed of this extra bit is going to be the final speed of this section. So let's try and find the final speed of this section here. So for this initial bit of motion, the initial speed was 0, just because it started from rest. The acceleration I just calculated was 1.96. The distance it moved was 1 meter. And I want to find the final speed. So we can work that out. 2 times 1.96 times 1 and square root it. So that's going to be v equals 1.9799. Okay. Now let's focus on this bit then. So u is going to be this thing here, 1.9799. And then I can do v squared equals u squared plus 2as of this section here. So it's going to be v squared equals u squared plus 2as. If I solve that with these variables here, then I can find that s, or actually for us it was x, wasn't it? But we can find the displacement. Was 0.2. Okay, so that distance there, x, is 0.2 meters. So in total, the height above the floor is going to be 1.5 meters plus the 1 meter plus the extra little bit of 0.2 meters. So the total 1.5 plus 1 plus 0.2. So it's going to be 2.7 meters above the ground. Okay. Sometimes they might ask you for how high off the ground. Sometimes they might ask you how high above where it started, but you can just give them whatever they ask for. Okay, so that's a pretty standard question you would get where there's two separate bits of motion, and there'll be some like that in the questions we're going to answer in a minute as well. So the questions I'd like to have a look at is exercise 10F. There's lots of Pulleys questions, and there's some with two sections of motion like we looked at in the last two questions as well.